Thank you for the introductory music. I've never had that before. So today I want to talk about our work on speech recognition, specifically focusing on automotive environments and the new Tegra K1 chip from NVIDIA. So if you work in the automotive area, you know how important speech recognition is now and in the future. It's very intuitive. You can sit in front of one of these systems and use it without having to learn how to use it. It allows you to have eyes-free interaction, so you can actually get access to information, perform messaging without taking your eyes off the road. And this allows us to have safe access to information while we're driving. Speech recognition in the automotive field typically falls into two components: an embedded speech recognition engine, which runs locally in the car, and there we typically deal with very small vocabularies and simple command and control type applications. And more recently, there's been a fallback with the connected car to cloud-based speech recognition solutions. And once you have the power of the cloud, you can do extremely large speech recognition with very large vocabularies at real time with high robustness. And this is very useful for point of POI search, other information search, and for accessing large amounts of information while you're driving. So from these two different speech recognition engines, we have very different solutions to them as of today. So typically, in our embedded speech recognition system, we have very limited compute availability. Typically, we're dealing with a single ARM processor or a multi-core ARM chip. We're on the cloud. We can use our cloud computing capabilities, which can be extremely large. And so typically, we can only use models that are small, maybe have 1 million parameters within the model, whereas on the cloud side, for our high accuracy, extremely robust speech recognition, we can be dealing with 30 million, 50 million, 100 million parameter models. And the more parameters that you have, typically the more robust your system is, which means higher accuracy, high accuracy in noisy conditions, and better performance over a variety of users. The additional challenge is dealing with large vocabularies. So again, with an embedded speech recognition system, we typically have, one is limited memory, but two, limited compute. And so we typically can only do speech recognition in real time if we limit the size of the vocabulary significantly. And so typical solutions out there today might have 1,000 words, might have tens of thousands of words, but they're typically quite limited in the vocabulary that the speech recognition engine can recognize and understand. On the cloud, however, this is different again. So you've got our large servers. We can do speech recognition with millions of words active, and this allows for very efficient POI search. And as you can see here, we're dealing with factors about 100 times larger or 50 times larger. The one area where embedded systems or embedded speech recognition engines today still outperform cloud-based speech recognition is in latency and sort of reliability as well. And so because we've got an embedded engine, we're not reliant on a data bandwidth from our car to the back-end servers, and so we are always on. We never get into issues where we don't have connectivity, and often we can get lower latency. And here latency is when the person stops speaking, how long does it take until we can finish the speech recognition in order to provide a response. And we can typically, on an embedded engine, get very consistent latencies of around 200 to 400 milliseconds, whereas on the cloud, in the perfect condition, you might get 200 millisecond latency, but this can easily extend to many seconds, and even in some cases, we won't get a response at all due to the variability in the bandwidth connection. So what could we do if we could change this? And so what we really want is a solution that we can use large models, which give us high accuracy and robust performance. We can use large vocabularies, but we can do this on an embedded local system, which allows us to have a system that's running continuously. We're not affected by any bandwidth issues and maintain low latency within the speech recognition engine. And this is sort of the goal that we would like to do in the work I'll present today. So in the past, we've been looking at how to use GPUs, and specifically CUDA, to accelerate large vocabulary speech recognition. And we've presented at GTC a number of times around this topic. And what we've specifically looked at here is looking at the components of a speech recognition engine that can be parallelized and implementing a new speech recognition engine from scratch that is optimized for today's compute capabilities. So rather than optimizing a speech recognition engine for a single CPU thread, as has been done in the past, we wanted to implement an engine that can be parallelized and perform speech recognition when we have thousands of threads available. And the figure that we show here is what of our compute we currently do on the GPU side and what on the CPU side. And so the entire speech recognition process, which involves a deep neural network computation, which you might have heard from on other talks today, and even the search process, where we do search over speech recognition graph, is performed entirely on the GPU. We do still leverage the CPU, however, for other components, including natural language processing and understanding, and we can do this on the fly while the speech recognition engine is performing search. So what I want to really look at today is, can we tackle these challenges of large vocabulary, large acoustic models, but still maintain speech recognition on an embedded system? And here we show the performance first of large vocabulary. So across the bottom, we have our vocabulary size, 50,000 words, 86,000 words, 500,000 words, 1,000,000 words, and show the performance across ARM and with the TK1 GPU for these different vocabulary sizes. And there are a couple of things we can easily see here. So even in the very low vocabulary case, by doing speech recognition on a GPU on the TK1, we can perform it at about 6 times faster than a comparable ARM-based implementation. And more importantly, as we increase the vocabulary size, we have a much larger system that we're doing speech recognition on, but the time required for speech recognition doesn't change that significantly when using a GPU. However, on an ARM or on a CPU, the difference becomes quite dramatic. And so in this case, when we are doing speech recognition with a 1,000,000-word vocabulary, on the ARM, we're taking more than 2 times longer than real time. On the GPU, we're still much faster than real time. And here we get a speed up of 13x, or 13 times faster than an ARM-based implementation. The other important aspect of this is understanding what is a usable system versus something that is not usable. And so there's a special number here, which is 1. And if we are faster than 1, that means we can perform speech recognition faster than the speed that the audio comes in. And so when we're doing interactive systems, we have to have a system that is faster than this threshold of a real-time factor of 1.0. And we can see here that on the ARM implementation, when we have a low vocabulary, in this case around 50,000 words, we can still do speech recognition faster than real time. However, as we increase the vocabulary, then the ARM is not able to keep up with the incoming audio. However, the GPU is not affected by this at all. The second aspect that we looked at here is the size of the model. So typically, when you're building a speech recognition engine for an embedded system, you have to use a small model with few parameters in order to perform speech recognition in real time, even given limited compute resources. And so here, we looked at taking a very small system with a 1,000,000-word parameter model, and this is what we typically implement in an embedded speech recognition engine, and then comparing the performance up until we have a very large model with 30 million words, and this is typically what we deploy in a cloud solution. And so again, we've got the performance on our TK1 platform, first using just the ARM processor, and second using the TK1 GPU, and we can see again a dramatic difference between these systems. So for the small model case, the GPU implementation is about 5 times faster than the CPU. However, when we increase up to a very large model, in this case our 30 million parameter model, we see a speed up of 12x. And again, if we look at our special number of we need to do speech recognition faster than the audio as it comes in, so this real-time factor of 1.0, we can see that using an ARM-based implementation, we can only do real-time speech recognition if we use a very small model. And this is how we've typically done in the past. However, with the TK1, we are now able to do speech recognition with the same model that we use on a cloud-based solution there locally on the embedded device. So using the TK1, we've been able to take a large model, similar to what we use on a cloud-based solution, and run it in real time on a local embedded system. We've been able to take very large vocabularies, in this case dealing with 1 million words or more, and can run this, the same solution that we're running in the cloud, we can now run on an embedded system. And we've got the small advantage in that now we've got a system that's embedded, it's always on, it's not affected by bandwidth back to the cloud, and we get a consistency both of usage and of latency when users use these systems. So the take-home message here for the first part of my talk is that we can rethink how to implement these systems given the GPU capabilities that are now available within vehicles. In the past, there's always had been this trade-off between the speed, the latency, and the accuracy if you're developing an embedded solution, but this is no longer the case. So the TK1 provides sufficient compute power to do cloud-based speech recognition, or the quality of your cloud-based speech recognition locally on an embedded system. The only drawback there is dealing with memory and being able to handle these large models. But we have shown that large vocabulary and fast and real-time speech recognition is now practical on this new hardware. And so far, I've been talking about our embedded speech recognition solutions and showing that we can actually implement a speech recognition engine that has the same quality as a cloud-based solution locally within an embedded system. But that doesn't mean we're going to get rid of the cloud. So when you have access to a cloud-based solution, it's extremely useful, both for speech recognition, in that we see how users are actually using these systems, and secondly, often for information retrieval and for other tasks, including email and messaging, etc., we are actually using cloud-based solutions, so if we have a network connection, we should use it. So when we're looking at ASR on the cloud, what we've been looking at is using GPU solutions to accelerate this as well. So on our cloud-based solution, we've optimized a system to run on Xeon Intel-based processors at real time. So using just a single core of an Intel processor, we can do speech recognition at real time and get an accuracy around 93%. If we incorporate a K20 GPU into this, we can get the same accuracy, exactly the same performance, using the same models, but now we can do it with only 3% of the utilization. And so this allows us to do numerous things. One, given the solution, we can now support multiple users on a single GPU compared with one user per CPU as in the past. Or two, we can go above what is possible today on CPUs and use much larger models that are impractical, that are not practical with CPU-based solutions, and use them in real-time systems because we've got the power now of these GPU-based solutions. So here we've taken a model that is even larger than what we typically deploy, and we can improve the accuracy slightly from 93 to 95%, but this is impractical to deploy on CPUs because it's twice as slow. So here, on a CPU-based implementation, the speech recognition is about 2 times slower than real time. So if I say something that takes 10 seconds, it will take 20 seconds to recognize it. So this is not useful for human-machine interface type solutions. However, on the GPU, we can see that we still have a lot of leeway in that with the same model, we can now do speech recognition at about 10 times faster than real time, and can even increase the model to make it much larger and not hit this threshold of the real-time performance. So the other thing that this cloud-based solution allows us to do is to perform speech recognition much faster than real time. And although this is not appropriate for human-machine interaction, for other tasks, you can be very useful. So here I'll show a short video showing our speech recognition engine, one running on your left-hand side on the CPU, and then on your right-hand side with our GPU-based speech recognition engine. Here we're using exactly the same models, we've got exactly the same performance, but we're just showing the speed difference we can obtain by implementing speech recognition on a GPU. So here we can see that in this case, we've taken about an hour of audio. On a CPU, it took close to an hour to transcribe it, but on the GPU, we can transcribe it in 2.5 minutes and not lose any performance in terms of accuracy. Okay, so I'll wrap it up here. Thank you for your time, and I'd like to open the floor for questions.
ご質問のある方、挙手お願いいたします。マイクを持ちます。
Hello, thank you for inspiring speech. I have one question. Yes. So the accuracy in the automotive area, that it depends on the noise that vehicle generate. How do you think the noise level on your test?
On my test or in general?
Yes. So actually, if we decrease, if we very quiet, the noise level getting very decreasing. But we have to consider the noise when we have to consider the noise level. So what do you estimate, or what do you think the noise level?
So dealing with noise is an important issue in automotive environments. And however, there's been a big shift in speech recognition just in the last 2 years with the deep learning phenomenon. And this, rather than estimating the signal-to-noise ratio or trying to pre-filter audio, the best approach that exists today is to model it within a single deep neural network. And so we obtain better performance today by doing no filtering, but training a deep neural network on noisy audio than we do from filtering with a human-optimized front end and then training a system based on that. And so there are other techniques that you can do about estimating on the fly what is the likely noise condition. But again, the best way to handle that is within the deep learning model, within the speech recognition engine itself. And we can talk a bit about that offline. There's some proprietary work going on in that area.
Thank you very much.
Thanks for the interesting talk. I'd like to ask for the more how to do for the model update. Since if you use for the cloud-based approach, it's easily to doing for the model update. But when you use for the embedded, it's really hard to distribute for the new acoustic model or vocabulary. Could you tell us for a little bit about your thought for this problem?
So I believe the right way to do this, even though with these new GPU solutions, you can do very large vocabulary on an embedded system. Typically, especially for automotive, the owner of a vehicle is not going to use 1 million different words. They're going to use a subset of that. And if you can pick the subset that works well for that user, you will get the best performance. And so our actual solution, rather than doing a purely embedded or purely cloud, are again these hybrid solutions, but pushing model updates as the user uses the system from the cloud to the embedded solution. And so one, you can do adaptation to the voice, adaptation to the car conditions locally without any connection to the cloud. But then when you're dealing with new vocabulary, you want to have this cloud-based connection so you can pre-grab or pre-gather words that are required and pass this to the vehicle or to the user as they are using the system.
Thank you.
はい、他にご質問ございますでしょうか。
Thank you. So from your slides, it's very clear that the TK1 outperforms the ARM very clearly. But what about in terms of cost? Because nowadays ARM is becoming very cheap. There are very small chips that are sold for very low prices. So what about the performance and cost?
So
ratio?
I think this more comes down to what your application is. So if you're trying to do something very basic, keyword spotting, or a command and control where you only have 10 or 1,000 words, then cost might be a factor. If you can get something running on ARM, that is the most cost-effective solution. But if you want to do something completely different, if you want to do something that's more natural, where users don't need to remember commands, but they can just speak spontaneously, we hit a limit quite quickly with these ARM-based solutions as of today. And sort of the cost factor that we've seen is currently we're getting similar performance with the TK1 to what we get with an Intel i7 for this specific task. And so we could either have a sort of a higher-end Intel or one of this ARM plus CUDA, ARM plus GPU systems, and that is sort of what we're dealing with. And even with speech recognition and other talks that you'll see around today, when you get into neural network processing, for image processing, speech processing, any type of signal processing, you're dealing with very well-structured but extremely high compute that you need to be able to perform. And so I think there's a limitation on current CPU architectures, but these GPUs and maybe future different architectures will be much more efficient for these types of models.
Okay, thank you very much.
Any more question? ご質問他にございますでしょうか。かな? Okay. Okay, thank you, Mr. Yang. Thank you.
Thank you.